Check 1 2. Check 1 2. 1.
1 minute 40. Wartet die also Sekunde? Ah, ne. Good morning, everyone, here in the Netherlands, on our location of Wageningen University and Research in Bleiswijk. And also good afternoon and good evening and maybe in the middle of the night to the rest of the world who is watching online. Welcome to the first edition of the Autonomous Greenhouse Challenge for our opening event of the hackathon. We have this year many teams over here in the room. We will later introduce them, and we will also have some additional tasks to fulfill this afternoon and some pitches to fulfill this afternoon. I would like to thank especially our sponsors, 10cent, Biobest, Quantified, Vreugdenheel Breeding Seeds, Saturn, Fluence, Lensley Substrates, Purpleman, Gebroeder Geers, and letsgrow.com. Without them, it would not be possible. So give them a big applause. So I'm Silke Hemming. I'm organizer of this challenge, and I will try to guide you through the program. And first on our program, I would like to hand over to Simon Fortuyn. He is the alderman of the municipality of Lansingerland, in which we are here in this region. Please, can I invite you to the stage and tell us a little bit why sustainability and innovations are so important for this region. Give a big applause to Simon Fortuyn.
Thank you very much, Silke, for your introduction. And I'm happy to be here on the International Autonomous Greenhouse Challenge 2024. Which is the fourth time. The challenge when creativity and knowledge comes together. And that's always the question. It's starting with why do we do things the way we do? And there are a lot of changes and also challenges in the future. First of all, I want to introduce myself. I'm the alderman of the beautiful community of Lansingerland. And I am stand-in for my colleague Leo de Hoek. Normally, Leo de Hoek, alderman colleague, is recovering from a medical surgery. So maybe he's looking, and we wish him all the best from here. I don't know where the picture is, or the camera is over there, I believe. But we wish him all the best. And I'm lovely to do and stand in for him in the place. What designs? What designs vision of the community of Lansingerland, especially Bleiswijk, the place we are here, is for our community very, very important. Since decades, we are active in agriculture. Greenhouse culture is our DNA. And the world is changing. And that is very, very important to know for each other, that we have to develop, but we have also to realize that all resources from the world are maybe ending, or we have to go with it on the other way. And innovation is one of the important things we have to do. And I'm glad that it's not only here by the WUR, oftewel the Wageningen University research, but we also working together with all enterprises in the neighborhood, but also all over the world. And not only that, we do it also with institutions like the Technical University of Delft or yes. Startups are very, very important because that are, let's say, the creative people, and we connect there the creative people with technology and knowledge. And at startup, what I said before, why do we do the things we do? And that's very important. The Autonomous Greenhouse Challenge is organized by the Wageningen University Research. Silke, thank you very much that you will do it, because it's very important also to connect the world. It's not only for Holland, it is for the whole world. And yes, today 23 teams from over the whole world create, let's say, a special thing about artificial intelligence, including, let's say, the machine learning, because we need people, but next to the people we need also technology. And artificial intelligence, or AI, it's new. For a lot of people it's new, and it's a challenge or is it a threat? We don't know. But otherwise we can use it in our greenhouse sector. And we see it in several startups, but also in practice. Today, 23 teams are in a competition, and that's lovely, and also challenging, and it makes me curious. And the most important things of that kind of challenges and competition is that we're sharing the knowledge and the technical innovation. And that brings us, or individual, or as a team, or as a company, to new developments. Because the sustainability is most important of the world. Everybody knows what I mean with sustainability. The resources, there is a discussion about energy, water quality. And the most important thing also is what we develop here or somewhere else in the world. Every place, every continent has its own roles. The water quality is different. Let's say the planet is different, but all the, let's say, energy or otherwise the weather is different. So we have to develop all the time to get the best results on the most efficient way. And in that case is artificial intelligence and also machine learning, but also, let's say, change the knowledge with each other, to share the knowledge with each other, to keep a good health for the planet, but also for yourself. After this day, you have a lot of pitches, I think, and I hope that on the end of the day, the jury made the right choice. But to say before, every 23 pitches are even worthwhile as the best, because it brings us on new ideas. And I think that is the most important thing that we can do. So when you're not at the best 5, because there are, at the end of the day, through the jury, selected 5 teams. And from the virtual world, and maybe they tested a little bit in a lab or something like that, that's the prize that you have to practice it in practice in one of the greenhouses here in the area. And I'm very curious about the outcome. But nevertheless, I want to thank you all for developing let's say, the technology, the knowledge, but also the goal for the sustainability for our planet. I wish you good luck, a nice day, 2 days, it is 2 days, and I have to go, but I want to say good luck, and also let's find out the best solutions for the future. Thank you very much.
So you are challenged. And that is the one, right? And you already heard we have a jury. And I would like to introduce our jury. Leo Marcelis, maybe you can stand up. From Wageningen University. He already is the 3rd time in the jury for this challenge. So happy to have you back. Thank you very much.
Thank you.
Then from Korea, we have Inbok Lee from Seoul National University. First time in our jury, but very knowledgeable on technologies. Very happy to have you here, that you came to the beautiful Netherlands. And I hope you have fun with the teams. And last but not least, Kati Stepper from the University of Ghent in Belgium. It's her 2nd time in the jury. And I introduced you for the as last because you will also tell us a little bit more about what autonomous greenhouses can do to enhance crop production and to save resources. So it's directly the time that I hand over the microphone to you. Thank you, Kati.
Thank you. Okay, thank you and welcome all. So I will explore here a bit and tell you a bit about the Autonomous Greenhouse Challenge and the history about it. It was all founded to explore the potential of artificial intelligence and to do what? To basically remotely and autonomous control the greenhouse climate, but also crop, and include for data inputs sensors. You know from being here, but also in the past, it's a worldwide international competition, an open competition. It's multidisciplinary, so that means that there is IT involved, technology involved, there is horticulture involved, agriculture involved, but also companies, startups, researchers, students, they all come together, they work on the challenge, and it's really a challenge. And the good thing is that we can develop by that new knowledge, insights can be developed. It's also a benchmark, so it's important what you do and will do in the next 2 days, and then for the winners in the next months. So you will create basically a benchmark. It's also a way of co-creation, of networking. So there will be a lot of fun, and there was also a lot of fun in the past. You see here worldwide, international, many sponsors, juries, participants. So to the sponsors, thanks, of course. And yeah, I will not read them all, but you see the picture, you see the overview. So the idea behind the Autonomous Greenhouse Challenge has always been maximize net profit. That was the goal of all the challenges. That means if you want to maximize net profit, that you have to create high productivity and on the same time use less resources. So in that case, you can maximize your net profit. The idea was to do that with the use of different sensors, and you see climate sensors can be used, crop sensors can be used, but also sensors to then automate irrigation. And then the second step, besides the sensors, is also to use artificial intelligence, because that is the idea, to explore the potential and the power of that. You see that can be unsupervised, supervised, reinforcement learning, can all be used. And in the first 2 editions, these things were combined. And in those 2 first editions, the participants were also allowed to now and then have expert knowledge and turn some knobs, let's say, to have then like an autonomous greenhouse control. But in the 3rd edition, it was fully autonomous control. So no human interaction anymore. If you look then a bit at the results, then you see, again, to remind you, it was optimizing net profit. But what came out from the first edition, that you see the different teams. You see also the red line, that is what the growers were doing. To give you an idea, the crop there was cucumber. And you see that one of the teams were better than the growers. The other ones, kind of neared it. But in all cases, there was 12% more production on average. So that means that indeed with artificial intelligence, that you can have, by maximizing the net profit, that you can have 12% more production. In the second challenge, the crop changed. So it was on small tomatoes. And there, almost all the teams did better than the grower. So we learned, or the teams learned, let's say. But in addition to maximizing the net profit, they could also save 20% energy use. So remember, exploring the potential of this artificial intelligence. So we see we can maximize production and have energy use, or less use of resources. Then in the, to go back, yeah. In the 3rd edition, then the crop was lettuce. Like I have told you, that was fully autonomous, so no interaction of the humans anymore. And all of them had maximum profit, and you see not a little, so 28% on average. So that means that indeed with artificial intelligence and including new technologies, that we can, like has been said before, we can indeed drive innovation and do good. This can also be very handy and nice because you see here from each of the challenge a paper came out, data sets came out. You can download these data and the papers, and they are very interesting reading material. And then to maybe summarize a bit what are the achievements from all the past challenges, but also you will now contribute to make this even going a step further. So there is a new community. You are now part of this new community, a new autonomous greenhouse community. We have shown, and you will also show us and pitch in the coming 2 days, that indeed AI can contribute to sustainability. There is a development of new sensors that fits then with this autonomous greenhouse control. We get new insights, also not unimportant. We get new insights on the performance of the crop, which can then again steer and drive technology. Unique public data sets, which is these days very, very important. And from the challenges, at least 4 startup companies resulted, so maybe amongst you others will emerge. And last but not least, there is also new infrastructure that gives them the opportunity to combine AI and horticulture for the development and validation of new technology. So, and you will experience that, well, not all of you, but the 5 that wins, they will experience that you can indeed use this infrastructure then and to come to the next level of autonomous control of greenhouses. And I think that's it. Thank you. Oh.
Thank you very much, Kati, to talk us through the former editions of the challenge. Which brings me to the most important part. That's the teams. You, all here, or online. And with that, I would like to hand over to my colleague Ping Lin, and she will introduce the teams to all of you and to the online audience. Ping Lin, floor is yours. The green button. You can see things on
Okay, hello, good morning. My name is Ping Lin. I'm one of the Wageningen organizer for the challenge this year. And I'm also one of the persons behind the mailbox communicating with all the teams throughout this period. So it's really nice to meet many of you in person today. And in fact, 3 years ago, I'm also one of the participants sitting here, feeling very excited as well as nervous for the hackathon event. So personally, I feel very much connected with the challenge as well as all the teams. So this year, as you can see here, we have the challenge has attracted many autonomous greenhouse enthusiasts from all over the world. We have participants from almost all the continents except Australia and Antarctica, while the latter one is relatively more reasonable. And in total, we have 23 teams. The largest team has 27 members, while the smallest one has 3 members. So average team size is around 10. And we have total participants of 237. So it's really a large group of people. And today, I already recognize some very familiar faces in the audience. These are the photos from the previous hackathon, and I think some of the people on the pictures is also here in the audience. It's really nice to see we have some old teams coming back with their new expertise as well as new vision. So first, I would like to present some of the old teams participating in this challenge. And of course, these are not only the challenge veterans, because there are also some previous participants coming back with new team members, and we will soon see their videos as well. And I really like what is written here, diverse in expertise and reunited in vision. Because this year in many teams, they are very multidisciplinary, coming from different backgrounds, computer science, crop science, mathematics, robotics, and so on. And now let's look at the organization. So we have teams from 62% of the teams are from the 62% of the participants are from the research institute, 30% are from different companies, and also 8% are from different organizations. And within these research institutes, in total, we have around 37% are students coming from more than 40 universities or research institutes. So next, I would like to present the introduction videos of these teams from the Research Institute.
Hey, this is Scott and Pavi. We are a team of 6 from ETH Zurich. We are 4 PhDs and 2 postdocs. We are all machine learning researchers, and half our team members have actually worked directly on crop management and related applications before.
So 2 of our team members are Dr. Matteo Tucchietta and Dr. Luca Corinzia, and they've worked extensively with crop management applications.
Yeah, and then we have the remaining 4, which is Scott, Chenhao, Leonard, and me, Pavi. So we are all PhDs in computer science. We work towards reinforcement learning and learning-based control strategies in the real world. So we are particularly interested in agriculture applications, and it basically fits the kind of problems we like to tackle on a daily basis.
Hello, my name is Felicia. I'm a PhD student, majored in agricultural engineering at Zhejiang University in China. Our team is Ideas. We have 6 members.
Hi everyone, this is Tao Lin. I'm a professor at the College of Biosystem Engineering for Science at the Zhejiang University in China.
Hello everyone, I'm Liu Wei, a postdoctoral research in agriculture engineering.
Hello, my name is From Mei. I am a PhD student major in agriculture engineering.
Hello everyone, my name is Ma Xunyi. I am a graduate student at Zhejiang University.
My name is Yanxu Wu. I'm a research assistant major in agricultural engineering at Zhejiang University in China.
I am Iman Hindi, a team member of Agrotech Innovators team. We are 3 team members.
Hi everyone, we are 3 master students from the University of Amsterdam. I'm Shan Xinrui. I'm Wang Yifeng.
I'm Yi Xiang.
Hello, I'm Yilei Huang. I'm a biostatistician by training, and I'm currently a PhD student at the Max Planck Institute in Germany.
Hello everyone, my name is Chong Fang. I'm the PhD candidate from Wageningen University and Research. I'm now in the beautiful greenhouse from the university, surrounded by my own plants.
Hi, I'm Shan Xinrui. I have a special spot at home, a mini greenhouse with temperature and humidity control. I'm very excited to join this autonomous greenhouse challenge and to learn more about it.
Greetings from the León campus of the National Autonomous University of Mexico. I'm Dr. Aaron Vélez, professor in plant physiology, and I am a veteran from the first autonomous greenhouse challenge that took place back in 2018.
Hi, I am Renan Malafos.
Hi, I am Uriel.
Hello, my name is Emmanuel Reyes.
Hi, my name is Antonio Capella.
Greetings everyone, I'm Amilcar, also a math student who contributed to the Autonomous Agriculture Project.
Hi, I'm Andres Christian from
CIMAT, Centro de Investigación en Matemáticas.
Hello everyone, I am Sergio, I'm a math student.
Our experience goes from crop modeling, Bayesian inference, and artificial intelligence. So, together, we are ready.
I'd like to introduce us as a team, Saxion University of Applied Sciences, the Smart Mechatronics and Robotics Research Group would love to join in this challenge. Our team possesses a unique combination of skill and expertise, computer vision, AI and machine learning techniques, robotics, but also a bit of crop physiology and experience in horticulture. We want to join, be part of the network and the community, and to meet the contestants. We want to exchange ideas and experiences. It would be really nice to get a chance to work with that state-of-the-art greenhouse technology. And besides that, yeah, we want to have fun in the competition and see how far we can get with our ideas. Thank you.
Hello, we are Team Smart Tomatoes and a group of 4 German friends who are currently spread across multiple locations in Europe. My name is Marcel and I'm currently located in the southwest of Germany in Stuttgart. I'm one of the 3 engineers in our team.
My name is Jonas and I'm 24 years old. During my studies in mechanical engineering, I focused on computational engineering related topics.
My name is Marcel. I am 24 years old and I'm studying mechanical engineering here in Karlsruhe with the focus on robotics and information technology.
My name is Michael. I'm also 24 years old and I'm studying horticulture in Weinstefan.
And that is us, Team Smart Tomatoes.
Hi, I'm Johnny Lee, Assistant Professor of Precision Agriculture.
Hello, I'm Kweku, and a member of the peer group.
Hi, my name is Fiti. I am member of peer group. I am working on and focusing on the intelligent robotics parts.
I am Emre Sanki. I am one of the members of the peer group. My study field includes intelligent systems, neural networks, system identification, and adaptive control.
Hello, here is Ziye. I'm from the team Tomato Nuts. We are a team led by the PhD candidates at Wageningen University, bringing up together outstanding talents from China Agricultural University and company and research institutions.
The technique we use for this is reinforcement learning.
Our initial plan is to use a kind of 3D reconstruction method.
Due to the plant growth prediction by AI modeling based on big database, I will provide my experience of tomato cultivation.
In order to make climate control in greenhouses more intelligent, we want to use advanced computer vision and robotics to monitor the growth process of plants.
Nice.
Nice. I hope you enjoyed the video as much as I did. But this is not all the teams, so I will come back later to present you the rest of the teams. So stay tuned.
Thank you very much. Well, give an applause to yourself. And I think it's really great. We got so many nice videos, as you already could see, and we really enjoyed watching it and to get to know you a little bit. And I really enjoy that most of you are live here now. So we have a short break of videos. I would like to introduce my colleague Steph, and he will tell us a little bit more about the challenge itself. Steph, the floor is yours.
Yes, welcome everybody. Nice that you are here with such a big group and also online.
You've already heard quite some information about the challenge from the previous speakers, but I'm here to guide you through what all of you have been doing. Of course, if you worked hard on this, you probably know what you did last 2 months, but for the audience at home, we give a short recap, and I'm also going to give some hints on how your teams performed, but the real score will, of course, be determined tomorrow. And I want to start with going really back to why are we doing this? And you've heard it from the previous speakers. We have some global issues that we really need to combat. It's really hard to find skilled people that have the knowledge to control a greenhouse the best way. But we do need more fresh food. The global population is rising, and it's really important that everybody has access to fresh fruits, and greenhouses can have a very big role in that. But on the other hand, we also need to be very careful in how we use our natural resources, so we have to reduce our energy consumption. These are all very big issues that need to be solved, and there is a possibility. We see everywhere that data and technology is used in all kinds of sectors, so that makes us think, why not in the greenhouse sector? And the problem is, it's not easy, it's a challenge, and the challenge we need to solve together. So we really need to bring all the sharpest minds together, so I'm very happy that you're here with so many, and to really see, okay, what can we do here, and how can we solve this problem? I really liked this morning what Simon said, the alderman. He said it's a challenge, so of course there's a competition here, and everybody of you wants to win, but you're really participating on solving a global challenge that we have, so I'm very happy that you all made it. And all these teams have been working very hard the last 2 months. So the 23 teams, over 200 people, to perform 2 online tasks. And for the teams, it started 2 months ago, but for us, it started last year. What we did last year is we did a pre-trial. We already grew some dwarf tomatoes here in one of the compartments, and you see the growth process here filmed from above. And we did that to gather data. We took out some of these plants and we destructively measured them. We got the information on how tall they are, how many fruits there are, and about their content. And then we took individual plant images and we linked the images to the plant traits. And what we did with that data is we built a simulator. We already have an in-house simulator, and we adapted it to this new dwarf tomato crop. And with those 2 tools, we gave the teams 2 tasks, a computer vision task and a simulator task. In this computer vision task, the goal is to estimate plant traits based on an image, because images you can take autonomously, it's non-destructive, and it's automatic. So it has a lot of benefits over human manual measurements. And it's essential to steer the growth process, because if you see what your plant is doing, you can take an action on it. So it's an essential step in autonomous growing. So all these teams got depth images, and I am very bad at visualizing 3D images, but what happened is that there was a camera on top of the plant, and you see the individual plants from the top, but you also can see how tall that pixel is, so you can look from the side and you can see roughly how that plant looks. And then based on this information, there were 4 properties of the plants that needed to be predicted. So how tall they are, but also how many red fruits there are, and that's of course very important because that's the thing we eat in the end. And to give you some results, here I present one of the easiest images on the left and one of the hardest on the right. And I based this on the top 10 performing teams. And what we see here on the left, for example, is it's quite a big plant, but it has a lot of clear leaves. They are easily distinguishable, which as a human, I think, makes it a little bit easier to predict. And also, there are no red fruits. And I think all the teams were perfect in predicting when there were no fruits. The harder part was predicting when there are fruits, because as you can see on the right, you have a top view of this image. There are many tomatoes, and some are red, some are still orange. It's a bit hard to distinguish, also because of the orange crate at the bottom. And you can definitely not see all the fruits. So you have to estimate how many fruits there are based on this single image, and that is just a hard problem. But teams did very well. And another interesting result is here. So this is the performance of the few teams that did best in this challenge. And what I did here is I sorted all the images. So on the left here you see images that have a very small fresh weight. And then on the right we have almost 100 images, the images that have a large fresh weight. And every dot is a prediction of the team. So you really see that it nicely follows the curve. So they very accurately predicted the small images, and we allowed a little bit more noise because we look at the percentual error on the larger plants. So it was very nice to see that it worked well on the whole spectrum of images. But what you also see is that there's an outlier here. All the teams predicted that the fresh weight of plant number 35 was way bigger than it actually was. So we go back to the data. We look at the plant, and our ground truth says that it is 39 grams, and all the teams predicted 80. So, but actually that is more realistic, because this is what a plant of 38 grams look like. So apparently there's something wrong in our measurement. Maybe it was a typo when we entered it in. Maybe because it's a very delicate process. We take the plants out, we measure them, we image them, we move them, we destructively harvest them, we dry them. So we do a lot of steps. And this really indicates why models are very important, and they can solve a lot of issues. And it's really nice to see that already now these models can be used to improve manual measurements. So they're already the first benefits. And then to give you a peek sneak of what will be announced tomorrow, these are all the team ranks. So these are all the scores of the 10 best performing teams. On the left, the best team with the error, and then the height of the bar is the total error. And what we see is that there are teams very close to each other. So team 8 and 9 and team 2 and 3 almost have identical scores. What we also see is that the height of the bars is not very different for all the teams. So all the teams really optimize the balance between these errors. Height seems to be a little bit easier, or at least have a lower impact on the final score. But really defining a good objective function is always difficult. So it's nice to see these results, and it's a really exciting that these scores are so close to each other. But that was not the only task the teams have been doing. The other challenge they had was growing tomatoes in our simulator. So we have Caspro Income, our crop and climate greenhouse and crop simulator. This is a visual interface of how that roughly looks. So we can simulate all the aspects of the greenhouse, so the indoor temperature, humidity, we can open the windows, the weather changes. But the teams didn't have this interface, they program it. So this is nice if you want to learn a bit on how to use these kind of models, but actually the teams, they directly access our API. So we have a model running on the server, and that server has been busy, very busy. So here I show how many simulations the team ran. And a simulation takes a few seconds, 3 to 4 seconds. And you really see that teams put our server to work. There's also a big difference, a big difference. Hold your breath until the last team. Just remind you that this was 2 months of simulations, and there are around 1,400 hours in 2 months. So the final team has been running basically non-stop, which is really nice to see. And tomorrow you will learn whether that was worth it or not. But at least our simulator has been tested properly, and that is really nice. And this also shows the importance of a simulator. This also shows why it's important to have a simulator, because in total 1.6 million years have been simulated. And I'm pretty sure that many of these simulations are not really useful to replicate in reality, but without having a simulator, you could never even get close to this number. So yeah, it's really nice to see that the teams worked so hard, and that our server worked so hard for the teams. And we have a lot of different results on the simulator. So I'm not going to give you the results, but what we looked at what the teams did. for the final task. And here you see a plot over time. So this is day 0, and it goes until a few days in the future. I'm not giving the numbers here. And here you see the fruit fresh rate, so how big the tomatoes are on the plant. And you really see that some teams started growing tomatoes very early and very rapidly, and other teams thought, well, let's take it slow and just wait until the end. There was a lot of difference. And it's nice to see there is not maybe not a single optimal solution. There are many ways to grow, and some are more economically efficient than others, and that's something you will learn tomorrow. I do have a bit of a breakdown of what is the most expensive part in our simulator. This is probably not what a real greenhouse costs, but in our simulator we saw that just having a greenhouse is pretty expensive by itself, and that heating was one of the bigger variable costs. But actually, this is all the past. What we're curious about is what's going to happen later. And that's why I made this visualization. I'm a data scientist. I like to make numbers visual, and I hope this works. So what we have here is dots. Each dot is a team. This is the best team. They are first in the vision challenge, and we give them 23 points. The next one, 22, all the way until, I think, 5 points. And there are a few teams that did not participate in this challenge, but we still give them a point. For the task B, we did the same. We also have the best team on the left and the team that did not participate on the right. And if we connect the dots, then we see that it's not, there's quite some variation. The team that performed best on the simulator is 6th in the vision, and the other way around, the winner of the vision challenge is 5th in the simulator. So that, if we combine those ranks, then we see that is really going to be an exciting day today. There are 4 teams in the lead. The first place is shared. So there are 4 teams in the lead, and there are 3 teams. Also, the 5th and 6th place is shared, and that's really the most important place. So there are 7 teams very, very close to winning. And actually, the other teams could still win, but then they need a bit of luck. But there are 7 teams that have it fully in their own control to win one of the last 5 spots of this greenhouse challenge. So the question is, how will they do that? Today, you will get a bonus task. My colleague will tell you a bit about it later. And you have to pitch in front of our experienced jury here. And based on those pitches, you will get your final rank. And then tomorrow afternoon, we will announce who will get access to one of our greenhouse compartments starting in September. So I wish all the teams a lot of luck. And also a lot of fun the coming 2 days. Thank you.
So that was a sneak preview. Did you recognize your own dot? We come back to the teams because we still did not introduce all of you. And I will give the floor again to Pinglin to talk us through the rest of the teams.
Okay, hello again. Well, as I mentioned, we have teams not only from the Research Institute, but also 30% are coming from more than 30 companies. And their participants work as growers, data analysis, software developer, as well as business developer, engineer, system designer, and so on. So without further ado, let's have a look at the videos.
It went too smoothly until now. It was almost unbelievable. So give us a few moments that we hopefully can solve that. In the meantime, maybe a question to the audience. Who thinks who is the winner on place 1? Wow. 2, 3, 4, 5? Who wants to be the winner? Yeah! I had hoped to see all the hands up. So, I'm looking to our technicians. Hopefully we will have some sound. Yes. Thanks.
Hi, I'm Andrew, and we are the Giant Tomatoes, a diverse group of innovators from around the world united by our passion to build resilient, sustainable food systems. Our team comprises experts from a wide array of nationalities and disciplines, including artificial intelligence, crop physiology, horticultural production, and systems engineering. This unique blend not only enriches our collaboration, but also positions us strongly in order to address the challenges of greenhouse production.
Hi, I'm Sue. Together, we are revolutionizing horticulture. Our team is a blend of industry and academic experts in CEA fruit crop production and plant physiology. We combine decades of experience producing dwarf tomatoes. We have a deep understanding of fruit quality, crop scheduling, and disease control.
Our team name is Superigo AI. The team has 16 members, specializing in areas such as computer vision, machine learning, IoT sensors, planting and agronomy, technology root.
All the requirements for tomato cultivation, including temperature, light, water, air, and fertilizer, are determined through a growth regulation model decision. Through the Smart Farmer platform, various data sources are sensed. Data fusion and diagnostic are performed. Intelligent control of environmental factors is implemented. Integrated intelligent irrigation of water and fertilizer is achieved. Intelligent robot operations are conducted. And digital systems for farm management, intelligent Q&A are established. This digitized system makes facility tomato production greener, more efficient, and smarter.
We're New Grow, and we're passionate about using and developing AI tools to produce more sustainable, profitable, and productive greenhouses. From TU Delft, we have Koti, Sebastian, Ioannis, and Salim, experts in data-driven modeling, optimal control, and AI. From Wageningen University, we have Julia, an expert in greenhouse horticulture with experience in both industry and academia. From Garden, we have Julian and other experts in data science, computer vision, and sensor technology for crop monitoring and optimization in greenhouses. From Berge AI, we have Camille and other experts in applying computer vision in various sectors, including horticulture. Our approach to this challenge involves combining physics-informed machine learning, reinforcement learning techniques, along with predictive control and state-of-the-art computer vision and data science methods to create adaptive and data-driven algorithms for autonomous greenhouses.
Trevor Hall, and I was graduated from University of London with a degree of electronic engineering and mechatronics. I'm on behalf of Team LEI. So it's a team from everywhere, but we're based in Hong Kong. We have been working for a company called LEI to provide smart farming solutions to help growers save energy and to boost up the yield.
Hi, I'm Leo. I'm a professional software engineer.
So I'm originally from Thailand. My background is in mathematics and physics.
My name is Francisco Cisternas. I'm originally from Chile. My expertise is in data science.
Everyone knows that one day crop production will be automated. No one knows when the day will come. We want to turn that distance one day into tomorrow.
Hello, my name is Kongbom Kim, and I am in charge of machine learning and programming in the KLGC team.
Hello, my name is Donghyun Lee. My part is automation and data analysis in this challenge.
Hello, my name is Junyoung Kwak, and I am in charge of control environment.
Hi, I'm Yoonju Jo, PhD student in crop science from University of Lincoln, UK. My PhD project is about wheat phenotyping using 3D and spectral images collected by the robotic phenotyping platform. Thank you.
Hello, fellow innovators and sustainable agriculture enthusiasts. My name is Ziyi Yang. I'm the team leader of Texas Agriculture. I'm a PhD candidate at Texas A&M University, specializing in biological and agricultural engineering.
Hello, I'm Chen Xu. The current position of mine is a data scientist.
Hello, I'm Guang Huilai, a PhD in material science.
Hello, I'm Ronald Hong. As a full-stack software engineer, I bring expertise in the full cycle of developing enterprise-level software solutions. Together, let's harness the potential of technology to revolutionize sustainable vegetable production. Thank you.
Hello, I'm Liu, the leader of Team Trigger. We are the team of 10 members, each possessing expertise in data analysis, AI, climate control, greenhouse management, and crop cultivation, including one student. A majority of our members participated in Korea Agricultural AI competition held in South Korea last year and won the top prize in both the hackathon and the tomato cultivation. In the upcoming challenge, our team is dedicated to pushing the boundaries of autonomous growing. We sincerely appreciate the opportunity and look forward to showcasing our best effort. Thank you.
The Greenhouse Steward Smart Facility Agriculture Innovation Team. Our team members have interdisciplinary and complementary strengths, involving horticultural facility environmental engineering, horticultural vegetable science, natural language processing, software engineering. We will effectively solve the problem of smart production for farmers, greatly assist them in intelligent management of greenhouses, and enable technology to empower rural revitalization. With the golden wings of technology, lift up the golden agricultural pole.
are Fravebot, a one-year-old startup based in the Czech Republic that manufactures robots and creates digital solutions for greenhouses. The scouting robot forms an integral part of an innovative ecosystem that collects image data about plant health, development, and morphology. Our team is assembled from experts and students in technology, plant sciences, and greenhouse production. Machine Vision team excels in bridging the real world and virtual reality with advanced data collection solutions. The artificial intelligence team is pioneering the digital twin approach using NVIDIA Omniverse platform creating cutting-edge algorithms for a variety of real-world computer vision challenges.
So these are all the teams, and we would like to thank you all for putting your efforts as well as creativities, making all these wonderful videos. And I wish you all good luck. Hope you make friends, progress, and don't forget to have fun. Thank you.
Yeah, but you know, apart from having fun, which I also appreciate that you spend some effort on it, you also have to work. Which brings me to our next speaker, which is my colleague Bart. And he will tell you what you have to do this afternoon in tasks of part C. Bart, the floor is yours. Tell them what difficult things they have to solve.
I will do. Thank you.
This is the click.
Yes.
You can see it there.
Yes. Good morning, everyone. My name is Bart van Moorwijk, and I have the honor today to present you the hackathon task. So, small introduction. In the last few months, you gained experience to optimize control in a greenhouse. You learned how to grow these nice-looking tomato plants by changing the light, temperature, screen, etc. Also, you learned how to estimate crop parameters from images like you see over here. But controlling a greenhouse is actually more, and we are missing one step over here, and that is crop protection. As a grower, you need to know if you have any pests and diseases in your crop to be able to maximize your profit. So the crop protection problem in a greenhouse, the scouting of pests and diseases is quite a challenging task. You need skilled labor, which is difficult to get nowadays. It's also time consuming, because if you have a large greenhouse, you preferably want to scan the complete greenhouse, but that's of course not possible. And of course, there's some bias. If I would go to the greenhouse, I would completely, I was not a crop expert, but I would completely see different things than the experts in the field. So one solution might be to solve this is computer vision. Oh. Yes. So the hackathon challenge for today is during our trial, we had this nice looking sticky traps from our sponsor BioBest. And these sticky traps, each hour they take an image, and then a grower could use it to how should I what actions do I need to take to reduce the amount of pests and diseases. So it's a high resolution data set, the images, and we actually want to focus on few-shot learning. And the reason is why is in the world of computer vision and AI, we keep using more and more data to improve our performance. And that's of course nice to get a better performance. On the other hand, we have to use a lot of resources to do so. And therefore, we really challenge you to only, you will get a few images and try to get really maximize performance with a limited amount of data set. So some more information about the data set. It will contain 5 classes. The first one is Bermesia. It's actually a white fly, and it's a pest in the greenhouse you want to avoid. And those flies, of course, they will stick on the sticky trap. Then we have the Encarsia formosa and actually Macrolophus. And Encarsia is inserted by the grower to actually to reduce the amount of white flies. And actually that's the same for the Macrolophus. It's inserted in the greenhouse, the Macrolophus, to eat the white fly eggs and to reduce the influence of the pest in your greenhouse. We also have Ciara in a class, which is actually a mosquito. You have to detect it as well. And of course, when you have this kind of sticky traps, a part of the species on the sticky trap will be unknown. And we want you to detect these as well, because at some point you might want to say, okay, if I have many unknown species, I might have to look at my sticky trap. So, as mentioned, it's really focused on a few shot learning. Therefore, your train set will be limited to only 2 images. So this will be a real challenge for you. The annotations will be in the COCO format, which is, I think, most of you known for you. And at 1 o'clock, we will open the dashboard. And on the dashboard, you can link to the data set. And there's also a document that really describes the idea of this challenge. There will also be a validation data set of 2 images and a test set. And to summarize the timeline, so at 1 o'clock you will get those 2 images. And this also contains some ground truth information, and also contains some example code how you should submit your result, but also how to evaluate your results. Then at 2:45, it's validation time. So then again on the dashboard you will be able to download 2 images of the validation set. In 15 minutes you have to process these images and send them again to the dashboard as you did before. And if you submit your result, you'll get the ground truth of those 2 images as well. So then you double your data set. Then of course you can have another 2.5 hours to improve your algorithm where needed, and then it's really time to test your algorithm. So at 5:45, we will release the 9 unlabeled images. Again, you have 50 minutes to process them and submit your results. So we have actually some small rules, and they're actually basically quite simple. It's allowed to use pre-trained models that are open source. It's also allowed to use additional open source trainings data, so you can increase your data set. It's not allowed to be influenced by human, which actually, of course, also makes sense. But it's actually not allowed to use non-open source data set. And the reason for this is some of you might be involved in this analyzing these sticky traps as well. And if you have your custom data set, you might have an advantage compared to the other teams. So we would really encourage you to stick to only the open source data sets. The winner, the team with the highest mean average precision will win. You will also get some code to evaluate on the training images yourself. And of course, the final scores, those will be announced tomorrow. Oh, I went wrong. Sorry. Oh, you removed it. Oh, thank you.
Thank you very much. Bart, stay close, because people might have questions. First of all, we will also send you a written technical document on this part C after we close this opening ceremony. So you can also read back what Bart just told you. But I would say I open the floor for questions which might be there. Who wants to ask some questions? Don't be shy. Yes, please. Maybe we can use the second microphone. Somebody is running to the back. And I will stay with Bart here, because probably he needs to answer that.
Where was the question? Yep. Hi, thank you for your explanation. I was wondering if the metric MAP is COCO MAP or MAP 50 or?
Yes, it's the COCO MAP.
Okay.
So this will be also, it will also be in the script, but it's based on the COCO, yes.
Okay, thank you.
Other questions? Yes, please. No, just wait for the microphone, because otherwise we cannot hear you.
What is the typical resolution of the images?
It's 1500 by 2500 pixels, so around 4 megapixels.
Whatever we call high resolution. More questions, please. Yes, Steph, there is a question here. Now, please always wait for the microphone because otherwise we cannot hear it.
So what kind of sample code that we probably get?
The sample code.
Yeah.
The sample code. What kind of sample code do they get?
Yeah, now it's for realize the annotations or is this something else?
What does the sample code do?
Sorry, it's only just you can have an input. So you just input folder with the training images and with the COCO predictions, and then the sample code will give you the result of your performance. So
yeah,
so that's what it does.
Good. Yeah, thank you.
How many times we can upload the validation data?
One time.
One time.
Okay.
Okay.
For validation, you just upload it, and we will get the scores. We will also have a screen somewhere to publish those scores, but you only can submit once. But of course, after you submit, you get a ground truth, so then you can run your own script afterwards as many times as you want.
Yes, we are planning to give some intermediate hints this afternoon, after the validation.
Can we make some submissions before the validation just to check that the format is okay?
Yes. Yes. Other questions? It's the moment to ask questions. Yes, in the back. Steph, if you can run.
I run to where?
Just about how to submit the answer. I mean, we classify the insects, and then what we have to do. I mean, it's also a JSON file as in the other challenge, or I mean, what you expect as an answer for the upload. I mean, because it.
So you have to classify. You have this bounding box prediction. If I understand the question correctly, so then you have to predict, of course, the bounding boxes, and you have to classify them.
And how do they send them back? How do they send them back to the dashboard?
So we classify
that's just a JSON format. So you just send a JSON to the dashboard.
So the JSON would say something like we have 22 bugs of this type and 15 of this type and so on, something like that. I will classify them.
Yes, so I'm really partly deaf, so for me it's a bit difficult to.
Yes. So the question is how that format looks like, what they have to send back, and I think that is in the sample code, right? So you get a sample code, and you can use that to send back your results. Yeah. Are there more questions? Anyone? Don't miss this opportunity. Okay, there is one more.
The test is not a large set of images.
No.
How will the seed, for example, affect randomness, or is that just, there'll be some effect of that? Is that just accounted for?
It's random.
Okay.
Other questions?
Hi, so my question is, what are we exactly trying to predict? We are predicting the class of the bugs, like recognize the different type of bugs, and are we gonna count how many of each bugs as a prediction output?
How many of the bugs? And
how many you have to detect them all, and how many there are. You can do some data analysis once you get the data set about the distribution of the classes. That's also part of the challenge to deal with the class imbalance and try to also get the imbalanced the fewer classes. Try to predict them as well using the bounding boxes.
They have to so they have to count the different bugs in the different classes, right?
No, it's not counting. It's really you have to detect them. So it's an object detection problem. That's also why we use the mean average precision to evaluate the results. So you have to detect them, and then of course, if you do object detection, you have to classify them correctly Otherwise, your score on the mean average position will be lower.
Right. So so we are recognizing different type of bugs and count how many, basically. Is that?
You recognize them and then you count them.
If I can add to that, I'm not in the screen, but it's object detection. So you really have to say on the image, where on the image is the bug. So you draw a bounding box around the image, and then you have to say which label it has, so which of the 5 categories it is, and that you submit as a JSON file.
Yeah. Okay, more questions? There are more here in the front.
I'm gonna stick here in the back.
Okay, good.
Okay, thank you.
We will answer them all. Try to answer them all.
Yeah, sure. I was trying to ask, do we have to develop the model based on the sample code? No? Like?
No, the model, we will not give you the model. We just give you a sample code.
The sample code is
How
only
to submit.
Is only for the validation? Like?
The sample code is only for the submission, right? So it's only example how you submit your result. You have to develop the model. We don't give you we don't give you an example for that. So hopefully you are all prepared for a few short learning. Hopefully you all did that before. Yeah, there were 2 questions here in the front, Steph.
Can we expect the same data distribution between the test and the train set?
Yes, but of course, when you do future learning, you also know that one image is not representative. Like you can never capture the complete dataset distribution with 2 images. So yes, test will be slightly different, but that's part of the challenge.
There is another question here in the front. There was somewhere over there, I think. Yeah,
I have one question here.
Yeah.
The question is, how many items do we have in the data set? Like, how many samples of bugs?
I don't know. It will be many because I do not know many exactly. But if you saw one of the example images on my slides, and then sometimes some of these images are more than much more than 100.
Okay.
So there will be plenty.
Thanks.
Other questions? I think there was something here, right? No. Okay. Other questions?
So are both the training and validation test set are taking picture? Are taken the picture in the same distance or the randomly taken picture?
Those are similar. So they all come from a same data set actually. So that's an advantage.
Other questions? Yes, in the back, Steph.
Sorry, it's back home. So I have a question from back home. So how do you calculate the mean average precision? I mean, if we classify the bug, there is a bug, but we misclassified it. How does the counting goes?
What is your calculation formula?
It's exactly the calculation is the COCO calculation. So it's the average precision and then the mean for all classes.
Of classes of what? Of the type or of position? I mean, it's not clear to me if we are getting because we have the number of bugs and also if they are of the one type or other type. How you calculate that?
If I answered your question correctly, if the box overlaps with more than 50% and it's correct, then it's a true positive.
Okay.
But if you will get the code, and then you can also see that it's just a COCO evaluation. And of course, when you use a COCO evaluation, you have the steps from 0.5 to 0.95.
Yeah, there is another question here in the middle.
First of all, are those pictures naturally occurring pictures or are they artificially placed, let's say the bugs?
They are naturally taken.
So there will be occurrences where 2 bugs are on the same box?
That can happen.
And
I don't know if it happens on the pictures. Do 2 bugs on top of each other?
To be honest, I also did not look really for 2 bugs on each other. But if you had paid attention on the example image, you saw that the unknown classes are quite big. So it was a fly. And there, of course, when the fly is really big, the bounding box is really big. So there can be a white fly inside it.
So we are supposed to be able to handle such situations, saying one bug is more obvious than the other, and then we classify that as the dominant bug.
Yeah,
okay.
but yeah.
Okay.
Yeah.
More questions? All clear for the moment? Again, you get the technical document. On 1 o'clock, you will be able to download the first two training, high resolution, very extended training set. And then you can go for it. That brings me also, I think, to the end of our opening ceremony. I wish you all a lot of success this afternoon for the pitches and also for solving task C. And don't forget to have fun. Don't miss out lunches, barbecues. Barbecues will only start after you have submitted task C, right? Because then we are sure you can drink the beer and whatever you want to do. So don't forget about that. And thanks for being here and have fun.